Good to go. I hope everybody is ready. Who wants to see more slides? Okay, good, because then you are in the wrong talk. Maybe I was too lazy, but I don't have any slides. We will need to do all of this live. Let's see what we have here. So we want to do some debugging, and before we dive into like what we're actually monitoring, let's quickly have a look at what we have actually built here. So if you've never seen Kibana, this is Kibana, but we'll get to that in a moment. What we're more interested in is our application that we have built here. So we have a Kubernetes application. Who is using Kubernetes? Who is using Kubernetes in production? Okay, that's a typical question. Probably you want proper monitoring when you do that. Let's see what we can monitor here. So we have an ingress. Your data is coming in here. It does a round robin between 3 instances. So on the physical level, I have 3 large instances on GCP, on the Google Cloud. And when our application receives the request initially, it is being served by a node application that is running behind Nginx. And we actually have a React front end to take that traffic. So that is kind of the front end that hits our application at first. And then we have 2 other applications where this traffic is being redirected to. So we have one Spring Boot application also running behind Nginx. And again, we have 3 of those as well. So we have 3 physical instances, and there is one running on each one of them, both for this front-end part and also for these 2 back-end parts. So we have a Spring Boot application with Java that is serving the traffic here, and it has a MySQL data store behind it. And then we also have a Python application that has Elasticsearch behind it, but I'm not going to go too much into the Python side. We'll mostly focus on the front end with React and Node, and then we'll go to the Spring application. Generally try to keep in mind the model, because we will get back to that when something is slow, what might be slow in our overall system. So we have the front end sitting here, we have our Java application, we have MySQL sitting here, and in parallel on the back end we have a Python application with its own data store. So this is all nicely separated. Then we have these little icons here, which are just hand-drawn as well. These are the beats. Who is kind of familiar with the Elastic Stack and the components? Okay, not so many. So generally, it was once called the good old ELK stack, Elasticsearch, Logstash, Kibana. So you have Elasticsearch, which stores the data, which is also widely used for full text search. So if you search on Wikipedia or Stack Overflow or GitHub, behind the search box, Elasticsearch is doing the search. But as it turns out, logs and metrics are also kind of a search problem, because storing them is the boring part. What you want to do is you want to find interesting stuff in them. That's why we always consider everything kind of a search problem. And in our example, how do we collect things? Basically, we have the beats running on our instances as... How would you run exactly one instance in Kubernetes per host? Yeah, the specific thing is a daemon set where you make sure you have exactly one copy running on each node, and that will then collect the information that you have on each instance. And what we basically have, we'll keep it relatively simple. We have these beats. The beats are like lightweight agents or shippers. They're written in Go, so you have native binaries. You don't have any runtime dependencies or anything. They're very lightweight. They're like forwarders. They will just take some information and ship it away. So we have file beat to collect your log files. We have packet beat to look at your network traffic. It's a bit like Wireshark. Who likes using Wireshark? Or who is using Wireshark? Normally those are the desperate days, right? When you have no idea what is going on anymore, and then you turn on Wireshark and look at random packets. Especially in Kubernetes and in a distributed application, this is hard. And PacketBeat tries to make that a bit easier by just running there, using the same base library, libpcap, and just extracting relevant information from the header. So for example, it would know, and we'll see that later on in MySQL, it know this was a request response, this was the query that was initially sent, this was the response set, and it took like 50 milliseconds or so to return that, and we could extract it. Metric beat could collect metrics either from your host, like CPU and memory, but it could also get metrics from, for example, MySQL or Nginx, like how many queries are you serving, and what is the overhead or wait time for your data database, whatever. All of these can be collected. Audit beat would do stuff like which processes are running and more like security events. And we have all of those running. So we have the beats running and collecting information. They forward stuff to Elasticsearch directly where we store it. And then we have Kibana, which we have here on the screen, to actually see what data we have in our system. So let's maybe start with the logs, because that's kind of the typical thing that you have. And that's not what I wanted. So let's say here, you can see in 1.5 days or so, we have 2 million log events. But this is a Kubernetes cluster with various namespaces, and we don't need all of that information. So what we are interested in is I want to filter that down on a specific Kubernetes label. So I have Kubernetes labels, basically the Kubernetes metadata. I have added that. And then I can just say this is equal to, and then I have my various applications. And for those of you who have done a bit more or demos with Spring Boot, probably you have seen Pet Clinic. All of this code is based on Pet Clinic. So I didn't write the entire application. I'm just reusing an existing application. I also won't focus so much on the application. It's more about the logging and what we got out of it. Basically, it's like somebody comes to you and complains something is broken, and you want to figure out what is actually the problem and what is happening in your system. So let's say I'm interested in the Pet Clinic server. And when I filter down on that, instead of 2 million log events, you only have 470,000. You probably still don't want to look at those by hand, but at least you have like a bit of a filter down here. Let's look at what we have in one of these events here. So this is a random one. I didn't really know what I would get. The first thing that you might find interesting is that we have various pieces of metadata here. And all this metadata can be used for filtering and searching. So the first thing, is that, by the way, large enough for everybody to see, even in the back row? Everybody more or less okay? Yeah? Maybe? Okay. So the first thing that sticks out is we have some Docker information here. So we have all the Docker metadata that we have, for example. We would see the image on which this is based, but we also have, for example, the labels. And we could see, okay, this is an infra demo, Pet Clinic, Nginx that is running here. We have all of that in here. How do I get to the Docker metadata? How could I add that to my logs? Because that's not really related to my logs directly. How would I enrich that? Yeah, via the shipper. How do I get it into the shipper? Yes. So maybe let's take a step back and look at how we actually set up FileBeat to get all of that data. Because, okay, we collect the data. We'll get a bit more into the data in a moment. But let's see where we got this from. So I have my FileBeat set up, and I'll start with the config map. So basically, I have the configuration here. And this is how you would configure FileBeat. And this is basically how we run it. So you see, this is the daemon set I mentioned before. So we make sure on every instance that we have, there is exactly one FileBeat running, collecting all the logs from that. And in the config map, I define how this should be tied together. So the first thing that we do here is, if you have a classical application, you probably write out to a log file. And then you just say, like, here's the log file, take that log file and collect the logs. How would you do that in a Docker or Kubernetes environment instead? Yes, you would write to standard out, because you don't want to explicitly mount files around and mount them from your application outside to the host and then back into the sidecar or daemon set. You want just to get that from the default Docker logs that I'm using here. The other thing that I'm doing here is I don't want to hardwire that and say like, hey, this container here, this is Nginx, and every time that changes, you need to change your configuration of how to collect the information or where it lives. So what we have here is we have this thing we call Autodiscover. And what basically the daemon set does is runs on the host, and with the Autodiscover, it looks into the metadata of the other containers to extract the right kind of information. And here you can see I'm defining two conditions. And the conditions are, if my container name is Nginx, and this is the infra demo, because there might be multiple applications running on my host. If this is Nginx, then I know, okay, get the default Docker logs, but also make sure you parse them and treat them as Nginx. So here we have a module Nginx, which will basically know, okay, this is what Nginx logs look like, and I will in the background then parse them and extract the right information out of those. And we do the same thing for all the different containers that we have. So for example, here I say, if my container name has MySQL slow log, then we know this is a MySQL log, and then we will parse it out for the slow log accordingly. If we have the pet clinic client, we will know, okay, there is Node and React in that, so we know how to parse those log files. And then we will get back to that. We can tag that with, this is the pet clinic client, and here, this is my Java application, for example. If it's called the container pet clinic server, then tag it with pet clinic server, and make sure you collect the right logs. How would I write out my logs to standard out so that I could collect them correctly here again? Hopefully in my log appender, right? So let's see, we have my Java application further down here, source main resources, log back. So all we do here is we define this appender, where we basically say, don't write this out to a file, but write it out to the console directly. And we're using a super simple pattern to actually write that out. So we have the log level, the logger, and then the message. What might be a problem when we try to collect that? Multi-line messages, yes. Because Java has this thing called stack traces, which is multi-line. And what FileBeat by default does is it always assumes that if you have one line, it's one event. Does one line of a stack trace make much sense on its own? Not really. So how would you put them back together? Yes, exactly. The trick is to never break it up, because breaking something up and then putting it back together in the right order is much harder than not breaking it up in the first place. So what we have here is, oops, that's not the file I wanted. We need to go back to the config map where we were in our pet clinic server. We have this thing here called a multi-line pattern. And the point of the multi-line pattern is it basically says like, every event that I have starts with one of these. So it's one, error, info, or debug. If it's not one of these, then everything that is coming after that line should be considered one event and should not be broken up. And this way we will make sure that we don't break up the stack traces in the first place. So it basically will read line by line, but it sees if it doesn't start with one, error, info, or debug, then it's the continuation of the previous line, and it will kind of like keep that together and not break up our logs. So this is kind of important to actually not screw up the events. So here, and by the way, what we didn't do yet is where does the metadata come from, because this is where we actually started from. We have these so-called processors, and the processors, they add the metadata. And you can see we have various processes how to add metadata. For example, we have, if you're running on AWS or Google Cloud, we can add the metadata and we will know stuff like availability zone, region, instance ID. We can collect host how do you collect those, by the way? Any guesses? Anybody knows? You know? So what there is, on AWS at least, there is this magic IP, which is 169 point something something something. If you query that, it will give you back your own information, basically. From the host, yes. But since we have that running on every host, it will know the right information. So basically, you query that IP address and it gives you your own information back. And we just cache that and add that to every single event. For the host metadata, we basically read some proc files from the Linux file system to know like you're an Ubuntu instance or a CentOS or whatever. We can add Docker metadata. What are we doing here? We just access the socket, which you will need to mount correctly. So it's accessible. And for Kubernetes, we just use the Kubernetes API to get the metadata. All of this is cached, so we don't need to do that for every event, but it will be cached. What might that in-cluster true mean? The file bit that we have here is running in Kubernetes itself as well. If you would install the file bit on the host directly, you could still get the metadata, but then you would need to tell the beat like, hey, there is the Kubernetes API. This is where you can get that information from. Whereas here, since we are running as part of the Kubernetes cluster, we know where the Kubernetes API is, and we can just enrich that metadata. And then we just, wherever we have configured Elasticsearch, we will store those events. And this is where all of this metadata is coming from. So you can see this is all the Docker metadata that we have. We have the host information. So this was the operating system. So you can see this is based on CentOS. We have the Kubernetes metadata, where you can see stuff like the namespace, the pod, anything like that. And under the cloud availability zone, you can see this is the information from Google Cloud, where you can see these are the instance IDs and the instance names, etc. So we can retrieve all of that information. And you can filter down on that, whatever makes sense for you. And here at the end, you have the actual event. What kind of event did we collect here? This must have been the access log. So we're collecting two things here. Or we're configuring Nginx this way that the access log is being written to system out, and the errors are written out to system error, and we'll just collect both of them and store all of them in here. And this is all the stuff that we have collected. This view is a bit hard to read, so we've added a link here for this is a kind of newer or nicer API, which is kind of limited. In that it just streams you the events. So here you basically see we have now filtered down on that specific pod. So these are just this is just the information for that specific pod, but you could change that here. You can just type other definitions or other rules, and you can just see these are all the events that we have collected from that one. So looking back at the information, how we collected, for example, our Java logs. Where was Java? But yes. Yes. Yes, so here, to keep it simple, we didn't include the timestamp. You could include that in the line here, but what you need to do is you will need to parse it out then. What are the options in the Elastic Stack to parse something? What would do the parsing? Yeah, you could do it with Logstash, but you don't need Logstash for all cases. For like simple cases, which are sufficient for a lot of use cases, like here, we have something called an ingest node, where we run the same pattern that you can run in Logstash, but you can run that inside Elasticsearch. And actually, I didn't show you that, but this is also part of this configuration here. So further down, we have the Nginx access pipeline, we have the slow log here, we have an ingest pipeline which runs in Elasticsearch. But this is exactly what you would define in Logstash as well. So the grok pattern, this named regular expression, this is how we parse those. We have that for the Java application somewhere, which should be super simple. This one here is a bit more complicated. So here we have the Nginx error pipeline, the MySQL error pipeline, and somewhere there should be the one for the Java application. If you need to have the timestamp in there, you would need to write the rules here to parse that out. So for example, whatever we have here, here we have a pattern and how to parse, for example, the Nginx access log. And if you have like a timestamp and the error level and you want to parse all of that out of your Java log, even if it's going to system out, you would need then to write this regular expression here to parse that out. Does that make sense? Well, it's so we are using common log formats, but it's just a regular, so it's just a named regular expression to parse it. So for example, to write the one for that logging format, you would just have word space timestamp or whatever you have there to parse that. So whatever you define, it would be just a few elements in a regular expression to parse it back. No, in our simple example here, the only timestamp that we have is from the log collector, because, well, we don't write it out from our application here. You could do that if you want to have, like, you might even want to have the difference between when is it kind of like generated the event and when is it being collected. But that's up to you. In our example, to keep it slightly more simple, we'll just assume it will be collected in a very timely fashion, so you see when something has happened. And this is really when it's being read and not when it's being processed afterwards. So the gap in time should be very small. And this is how we collect all of these logs together. And then you have something like this view here, which shows you all the logs for this specific pod. But we did tag the instance we did tag the different logs when we collected them. So one thing that we can do is we can add a second condition here. And we said we have the tags. And luckily, this also gives you all the suggestions. So we say equals. And then we can say, is this a pet clinic server or is this a pet clinic client? And I'm only interested in the pet clinic server. And these will now just be the Java logs from our application. And if I look at those, no, I don't want another end. These are enough conditions, these two. Come on, run that and tags pet clinic server. This is not what I want. And tags equals pet clinic server. Now you just have the Java logs because we tagged just the Java logs with this pet clinic server. And here you can just see these are the log levels. You can see here our multi-line statement hasn't been broken up. It's just one big event, one very big event. And here you have the next ones. And you can just see how many events you had. You can scroll through them. You could filter them further down. On the right-hand side here, you can see approximately by this shape how many you had over time, just to see what you have in your logs. But you could also just search through them. But this was pretty simple to see what we have in our application here. In this one, you could also add any filters that you want to have. For example, if you would want to exclude everything that is being collected by either the FileBeat module for Nginx or MySQL, you could add that as well. For example, we have a field FileBeat module, if I'm not mistaken. And if my network is working out, file set module. And then you can say is not one of, and then it says Nginx and MySQL. So basically I exclude those logs, and if I filter down on those, you will get the same information. This is then just a Java log, but it's a bit harder to read because we have so much metadata here. But you can see here, warn, these are all the events that we have. Since we parsed out the log level, you could, for example, also see what is the distribution in our log levels. And you could see 73% are warns, 19% are errors, etc. You could also filter down on those as well. You just click the plus here. And then you will just filter down on the errors. And you can see we had 800 something errors in our Java application over time. And those are the ones we have collected here. And then you could just have a look like, hey, whatever went wrong here, something in my SQL query was obviously wrong, and that broke it. Bless you. Okay, so this is how we collect the information, and this is how we tie together the beat with the rest of the application. And I can show you metric beat and packet beat as well, but the configuration approach is the same. So you basically configure like I want to collect this kind of thing, and then you run it as a daemon set once on the host to collect the information. Let's change gears a bit and go a few levels higher, because maybe your users complain about the site being slow and you want to figure out what is going on. You could start looking at the metrics, but that is probably very low level. Going a bit higher level where you could go is tracing. Who is kind of familiar with tracing? Like Jaeger, Sipkin, something like that. What you basically have is you have an agent in your application, and the first time a request hits your application, you give it a unique ID, and then you follow that request as it goes throughout your system, and at the end you collect what has happened in your application, and then you aggregate that together. We have a very similar solution, which we call APM, Application Performance Monitoring, which is also just an agent that you add to your application. And that just follows the users as they query your system and collects, like, from a user perspective, how does my system behave? And we have that for Java, for Node, for React, for Python, and quite some others, but those are the ones that we have in here. Just to give you an idea, since I assume most have a Java background here, how would you add an agent to a Java application? Or a Spring Boot application here in my example. So this one is actually baked in my Docker image of the application. So we have the wherever I put my container here. Application property. No, this is not the one I want. Sorry. It's not Kubernetes, it's this one here. Here's my Docker file. So here in my Docker file, this is where I take my application, and basically what we do is we run our jar, Java jar, and then we add a Java agent. And the Java agent that we're adding here is exactly that APM agent. So the nice thing about the tracing is you don't have any build dependencies or runtime build dependencies or compile time dependencies. You can just add this agent for tracing at runtime afterwards. So you can just develop independently of that. And once you put it into production or development, you can add the agent at runtime to collect the metrics that we are collecting here. And this is unfortunately super hard to read. I hope this is still visible. But for example, how to configure that is you have some settings, for example, in Spring, the JPA settings, and at the same time you have some APM settings where you just say, this is my service and this is where it should report, etc. And in your Kubernetes configuration, you can override all of these from your Docker file with environment variables afterwards. This is how this is being tied together. And let's see how that actually looks like. So this one here, this is not a Gantt chart. This is the tracing, because you can see these are the bars from our application. You can see here, these are all the applications that we have running. So we have the front end, the Node backend for the React application, we have our Spring Boot application, and we have the Python application, but it doesn't really matter. And we have all of these agents, and they can collect, like, how long do the requests take and how many are there, etc. So let's look at our Java application first. And you can see here, everything looked pretty much okay, except for this weird spike. And we would be interested in what happened here. Like, why is there such a spike in my application? Or actually, if I zoom out a bit, this is generated historic data so that it looks kind of nicer. Let's look at it here. So you can see, let's stick to this day, so you can always just zoom in like that. This looks kind of weird, or this is not the way you want it to behave, because this is the response time. You can see the response times are mostly okay. Like, you can see the 99th percentile is 100 milliseconds, that's fine. But every now and then it spikes up to like 700 milliseconds. That's not really where you want to be, right? So let's see what is happening here. Down here you can actually see which requests were being run. Let's dive into one of these here and just look at this one. So you can see there is a very clear spike. You can also see here you have the requests per minute. So you didn't have more requests, because sometimes you just have more requests and then everything slows down. But you can very clearly see here there were the same requests. There were no more requests here when you had this spike than before. So the spike must be independent of that. Let's look at one that was very slow, or let's zoom in a bit, because you see right now we have the response times around 100 milliseconds. If we zoom in more, the response times should go even higher. And you can see now it's really getting bad. Like, here there's something bad happened here, and we don't really know why. Let's look at what is happening here. Basically, these are all the queries that happened. The height of the bar shows you how many requests did you have, and the x-axis shows you how long did they take. So for example, these were the fast requests. Those took like 100 milliseconds or so, or 49 milliseconds to 73 milliseconds. Looking at that pattern down here, what do we have? What is that from database perspective? N plus 1. When you run one database query, so you run one database query, and based on this data, you then start running more and more queries to fetch all the relevant data, which is a different problem which should be fixed, but because you probably can write one more intelligent query than writing 100 queries or whatever we have here. But this is still fast. So the fast request looks like this. Let's look at one of the slow requests. So we have one request here that took 1.4 seconds. If I look into that, you can see it's the same pattern. It just took longer. So the slow request, there's nothing really obvious in that request. Going back to my Spring application, okay, we see this was slow. Let's see if I switch application, if another application is impacted by that as well. So if I head over to my Node application, for example, you can see the Node application has exactly the same spike here. Where does that point, basically? Yeah, it's probably something on the instance. It's not really in the Java application and not the Node application, but it's something on the instance that is kind of troubling us here. Let's see how we could figure out how our instances are doing. So I said we have metric beat, which collects the system resources from your instances. And we have an infrastructure UI that looks like this, where you can see, depending on your view, for example, we have 3 hosts. That doesn't show you very much. You can look at the Kubernetes level. You can see the CPU usage. There's one that looks slightly more busy here. This has 13% CPU. The others are all rather not doing so much. These are the pods. You could, by the way, group them, for example, by node. Since we have 3 nodes, you can see this is the distribution. So there's not really an outlier per node, but there's one pod that is a bit busier. And then we could dive even further and say, I want to see that down to the container level. And if I zoom down to the container level, let's break that up by, I don't know, by host again. You can see these are my hosts. Probably the hotspot is very clear now. This one. And you can see this is a MySQL instance. So something is up with MySQL, and that's why everything is slow in my system. You can from here view the metrics of this specific instance or the logs of this instance. Let's look at the metrics to see what is going on. And this here, unfortunately, has a very annoying bug that has been fixed since then, that it always jumps to the current timestamp, which is not when we had our bad data that I added here. So we need to... Sorry? I will stop touching anything. Okay, thank you. So this is the right time frame that we want. Let's zoom into that one here. You can see the memory usage is continuously growing, but what is even weirder is we have these CPU spikes. So something is probably up with my application. And I want to figure out what that is. We have built some dashboards to actually dive into those as well. So let's see one of these dashboards. So we already have the hunch that this is related to MySQL. I want to kind of like take another look at this now. So for example, here you can see we have 9 instances running. This is all the data from our APM service, but we've just put that together in a custom dashboard that you can do. What I would be interested in is, let's say I want to see only the requests that are very slow. So the 99th, bless you, the 99th percentile. And then you can see very clear spikes here, and here, and here. And then you could look at which application is doing that. So everything I click here is filtering down just on that information. So for example, I could look like my Spring application, yeah, they have exactly the same spikes. So this is something, the 99th percentile is of my slow responses is related to my Spring application. Is it related to my Node application as well? Yes. This is also slow. Is it related to my React application? Not really. Here you don't see them that clearly. Is it related to my Python application? Also not really. So what do the Node and the Spring application share but not the Python application? The MySQL backend. So probably it's really MySQL. So we should have another look at MySQL. Luckily, we have also built a MySQL dashboard for that. And again, this is file beat, metric beat, and packet beat combined. So the top row here is a bit hard to read. Let's make that larger. You can see this is how many tables we opened, average threads, etc. So these are just some statistics about your MySQL instance. No, this is not what I wanted. I want to make that smaller again. And you can see this is basically over all my instances, how is CPU and memory usage doing? And what I want to do is I want to limit that to the pods that have MySQL. So we can just filter down here MySQL, and we have in that cluster we have multiple demos running. Cyclops is not the one I want. We want Pet Clinic, and we have 2 Pet Clinic instances. Pet Clinic, and you can see here we have these very clear spikes again. Something is wrong. And you can also see we have spikes here, and you can also see the spikes here. What is that? And then you suddenly see, oh, it's probably the database backup. Looking down here, which were the top processes, you see database backup and database sync are probably very prominent here. So probably you have some background job in MySQL running that is killing your performance here. And you can also verify that by looking at the actual logs. So here we have a link to the logs UI again. This is filtering down to the MySQL instance now. And here, for example, we are parsing out slow requests. And I'm interested in the slow requests. Why is MySQL actually slow? So what you can do is you can just say and MySQL.slow query. And I'm only interested in the queries that take more than X seconds. So I filter down to that field. How did we extract that field from the slow log? We had the ingest pipeline with the grok pattern that just parsed out how long that took. And basically I'm saying this should be larger than 30 seconds. So I'm only interested in queries that took more than 30 seconds. And when I run that, you get only, and you can see these were very, like, they run at specific intervals, so probably it's a background job or something that is running here. And you can see this is the actual query that has been running. And you can also see how many rows did we send and how many rows did we examine to generate that report. And that is one heavy query that you probably want to dive into and fix then. So that's not going to make you happy otherwise. Okay, since we have 12 minutes left, what else could we do? Let's see. Let's have some more fun with our application. So let's assume a user calls us and complains that their application is slow when they access the site. And well, we don't like our application to be slow, so let's take a look. Let's make it this time frame again. And you can see these are the requests. We had these spikes because of the background job, and that's when they were slow. But we have a specific user that complained that their requests were slow. So we could just filter down on the requests for that one user to see how they were doing. So we have context, user name, and the username that we had was, I think, something like come on, refresh. There should be a user called come on, auto refresh, don't leave me hanging here. I think this was it. Let's see. No? Okay, let me cheat. Let's say I don't, like, we have the username that we had here. or let's take this entire query here. I don't really see my typo right now. What? Yeah, that I'm slightly confused right now because I'm on the right date. Ah, but I'm on the wrong service. Because we need to pick the right service to actually make that work. So let's see, our user complained, and we have, for that user, we have 2 services which were hit. And you can see indeed, this one was pretty fast. The Node application was pretty fast for the user, but the average response time of 2-point-something seconds for my Spring application, for my React application, that's not really great for the user. So I would be curious what happened to that specific user. Let's look at the request. You can see the only requests that we had here were this one here. So let's zoom in a bit. So the user tried a few times, and these were the requests. And you can see all the pages were kind of slow. That's not great. Let's look at one specific one. So here you can see all of those were slow. And you can see, bless you, these were my SQL queries. These were all fast, but this one here, the initial one, was rather slow. And this is the React application. So this is client-side rendering. Any guesses what might be the problem if the initial rendering of the page is very slow? No, it's not really big photos. Let's have a look at the user. Let's see. The user here, you can see this is the username that we have collected, and we have also collected some other information here. And one thing that is kind of sticking out here, that we have a not so current browser. So maybe this user is just using a bad browser. And we extract all of that in every single request. So we can now change in our React application, instead of saying this is the specific user I'm interested in, we could say, for example, I only want to see the user agent that we have, and the user agent that we have is Internet Explorer. And then when we run that query, we see there were multiple people doing the requests, but all of those were slow. So it looks like, from a client perspective, our React application works okay on modern browsers, but not so okay on older browsers like Internet Explorer. And we'll need to figure out, like, either we can fix that for those, or we just exclude those browsers or tell people to upgrade and use a proper service to avoid situations like that. Yeah, not so great. Okay. Oh, we have still a few minutes. We can try to look into one more thing that might be interesting. Ah, that's not what I wanted. I want to stay on the same time frame, more or less. Let's say we have 26 to 28. These were when my slow requests were. We look at our application. No, we don't only want to have those. We want to see all of our requests. Once again, let's start with the React application. And let's dive into this one here, because I see a weird spike. Looking at this one, from the front-end perspective, our application is kind of doing okay, except for this one here. And I would be curious what happened here to my system. So if I dive into that one, let's look into that one. We see some spikes. Let's dive a bit more into those. You see some spikes in your application. And what is sticking out is, you see here, the page load time is 3.9 seconds, and the 95th percentile is 13 seconds when we update the owner. So let's see what is happening when we update the owner. Updating the owner, you can see we have some requests here. Let's look at the fast request. This is what a fast request looks like. Okay, we have a few database queries, but that's okay. Let's look at the slow request. And can anybody see the main difference between the two? This is slow. And this is, let's take this one, this is fast. Or this is not a good one, let's stick to this one. Sorry? Yeah, we have the n+1, but this is actually the fast query. What is taking the most time in the slow requests? So you see we have our three pieces here are being used. So we have the React application for the front end, we have the Node application, and we have the Spring application. And where we are spending most of the time is how to read this. Which part is where are we spending most of the time here? Validate zip code, exactly. So let's click on validate zip code. Let's look at the actual request of that validate zip code. So we can see that full request here. So we filtered down on that one. You can see the first thing that sticks out, this gives you a 400 back. So the user got an error back. And you can see we spent a lot of time. We spent 99% or so of that request of the 12 seconds in that method here. So that's weird. And we can also look at the request. We only collect the headers here and not the body. We could, but for performance reasons, we don't collect the body. But we can see the response. And in the response, we can see we have an error. Is anything sticking out in the response code here? Yeah, the zip code is very long for a zip code. I'm curious. Looking back at the validate zip code, we also have the reference here to the validate zip code Java at line 33. So this keeps track of where is the code actually, or which method is being called to cause that. So let's switch over to our application. And I need that class. So this is the class where we went, where that was referenced. In line 33, okay, this is just returning the match. The one thing you can see, this is just validating the zip code. And then when you actually look into it, what you will figure out is that this regular expression here is a really terrible regular expression, and that is taking up all the time. So if a user adds a very long zip code, this regular expression will take like 10 seconds to run. And this is why that request was so long. And this is kind of a nice way to figure out where you're spending your time by just collecting all of that information. Yeah, the joy of regular expressions is always there. Okay, so we've seen quite a lot of stuff. Where should you go from here, or how can you replicate what we have here? So to set up the beats, we have in the GitHub repository of beats. Let's make this slightly larger so you can read it. So in the beats repository, we have a folder called deploy. And in deploy, we basically have the recipes how to deploy this both with Docker and with Kubernetes. And then if you click on Kubernetes, you can see, okay, this is the general setup, and here we have like a more elaborate setup. And you can see we have the config, we have the daemon set, role binding, role, service account. So you have all the best practices how to configure this and put this into Kubernetes. And you can then just use this application to bring this to your own application. So you can see here we just have some configurations. This is how to add the metadata. And these are, for example, the processors that we want to run, etc. So here you have all the configurations for that. How do you tie the tracing from APM into your application? That depends on the programming language. So for Python and JavaScript, for example, it's a build time dependency. So you need to include that when you build your application. For Java, it's just a -java agent that you can add at runtime. So this depends on when you run this. And this is how to combine that. Okay, we have 3 minutes left, and that's pretty much it, I think. Yes, so we have the address resolver, we have the source, we have the requirements, and in the requirements, no, give me a second, this is not the one I wanted. Is it this one? So we have the configuration for APM, and isn't it? There is somewhere in here, I'm not much of a Python person, we do have the Python dependency then to actually load the tracing. But it needs to be a dependency in here. For example, for the front end in JavaScript, you have the client, and you would have in the package JSON, you would have the, somewhere there's APM here. This is how you would include that. So for JavaScript and Python and all these interpreted languages, it's a build time dependency that you need to include. For Java, it's -Java agent that you can just attach at runtime. Those are the main differences. Other questions? Yes. The APM is open source. The only thing that is what is not open source, it's only free to use, is this specific visualization. So this visualization here, it's not under an Apache license, but it's free to use, so you can just run that yourself. I didn't touch on any commercial features. So everything I've shown is either free or open source. We do have stuff like machine learning, which could detect these anomalies automatically, so you wouldn't need to wait for users to complain. Those are under commercial license, however. So you could just have like something that learns what is normal in your system and could then alert you that, hey, suddenly the response time of your service is much slower than before. Or suddenly you spend much more time in one place where we didn't expect it. Stuff like that is possible, and you could then just automatically get an alert by email or whatever, but that is not in the free version. That is how we earn money, which we also need to do somehow. But everything I've shown here, the beats and the APM agents, they are all Apache licensed. And the visualizations here, these three are free to use, and everything else was open source. Yes? Yes. We also have, this is pretty new, but we also have Openshift integration, so we can also tie into the Openshift metadata. Not just Kubernetes, but also Openshift. I don't think we have a recipe for Openshift, to be honest. Though my Openshift experience is pretty limited. I think you should be able to reuse most of the Kubernetes recipes anyway. But yeah, we in our documentation, so it's somewhere file beat Openshift config. It's somewhere in our documentation. Let's see if I find that, or maybe I don't find it so quickly. It's in the metadata filter and then configure the output. Add cloud Kubernetes Docker host. There was something for Openshift here. Give me a second. Yeah, here's the Openshift configuration that you can use. So it's in the docs. This is the general idea. No. I especially for this use case, I'm not sure it makes much difference at all. General question, no. I have the feeling it depends a bit when you started using it, because there was a time when Logback, before Log4j2, like with Log4j1, I always had the feeling there was a favor for Logback because of performance reasons. Since Log4j2, it's probably not the case anymore, but once you started using Logback, there probably was not enough upside for Log4j2 to actually make you switch. But it's probably a bit more of a taste question. Especially if you just write out to console and have a very simple pattern, I don't think you would feel much difference. No, this Well, just make sure you have a pattern that you can parse back easily. Mm. Right. As long as you can, if you then treat them accordingly when you parse it back, because the multi-line patterns that I was using were based on the log levels, so you would need to adjust that accordingly. But yeah, otherwise it doesn't make any difference. If you use MDC, for example, the map diagnostic context, you would just need to adopt the regular expression to actually parse out the structured fields that you have. So all of that should be pretty easy. Yes, so what you would need to do is you would write out JSON to system out, and then you would need to tell the file bit, hey, what you're reading is actually JSON, because then it would read that and have it in a structured format. That would be the ideal way. What some people also try to do is they would say like, hey, my log appender should write to, for example, log stash directly. Log stash directly via TCP. The main downside to that is if your network is down or if log stash is down, you don't receive any logs immediately. Whereas if you write it basically locally to console out, you will always write them out, and even if Elasticsearch is down or if FileBeat is down, they will then at some later point come up again and then see, oh, in the log file I have sent everything up until here, and this is the rest I still need to send. And then you can basically backfill. And you can also still locally look at the log files, whereas if it's only over the network and the network is down, you will not be able to see any logs. That's No. So we are using the default log, which is going to var lib docker id.json, I think. And we are basically just tailing that file. Because what you're doing when you look at the Kubernetes filebit config map, what you're saying here is type docker. The bit will know on your operating system where this file lives. And then it knows this is what to do with that file. And it can automatically enrich the metadata because, for example, it knows from the ID in the path, it knows to which container this log belongs. And it can use that in the lookup then to add all the metadata, because it basically has that mapping in the background because of the path.
It's not running inside the pod, but inside the host.
Well, no, it's a daemon set. So it's kind of like you have one pod, another pod, and then you have one instance of FileBeat running on the host. That is just collecting that log file, enriching it, and then shipping it off. But it's not, you would not package FileBeat into your pod, because if you want to just update FileBeat, you don't want to redeploy your regular application. You kind of want to have that decoupled. The APM agent, yes. So the APM agent needs to run with the application because it's part of the application. But the beats would run as a daemon set just once on each host, or you could install them directly on the host if you prefer that. Don't see much point, but you could. And that's all there is that you need. But you don't have any other tight coupling between the systems. Sure. I think we're out of time. Thanks a lot.